Welcome to this briefing. Today, we're taking a really fascinating journey into the very architecture of artificial intelligence. In this explainer, we're going to dig into how the energetic paradigm, or EP for short, takes this almost magical, abstract concept of AI emergence and turns it into hard, measurable engineering. If you follow AI capabilities at all, the word emergence gets thrown around constantly, usually as this speculative, maybe someday promise. But today we are getting into concrete, falsifiable tests.
Okay, let's dive into this experiment. We're going to start off by unpacking the myth of weighting. Then we'll walk step by step through the actual S0 to S4 experiment. From there, we'll cover metrics under perturbation, lock in on the S-star stabilization threshold, and finally wrap up with engineering emergence today.
So Section 1, the myth of weighting. This is really about a philosophical accident versus engineering reality.
For a long time now, the industry baseline has basically been a massive weighting game. There's this pervasive idea that if we just wait for bigger, more massive models, they'll magically start showing emergent capabilities on their own. It frames emergence as a happy accident we just hope happens as we scale up compute. But that leads us directly to a core, tension-building question. Does a structural strength threshold exist at the inference level? This changes everything. We're no longer dealing in philosophical speculation about what might happen one day. We are framing this explainer as a rigorous scientific inquiry. We absolutely need to know if structure itself creates a measurable tipping point.
And that brings us to the core thesis for today. Please, if you take nothing else away, burn this line into your memory. Bigger models wait for emergence. EP already engineers it. The energetic paradigm doesn't wait around. It actively engineers the exact structural conditions required for emergence. We're talking about coherence, path discipline, attractor formation, and stability under perturbation. It is a massive, fundamental shift from just passively observing to actively architecting.
Moving right along to Section 2, the S0 to S4 experiment. Let's establish our independent variables and get into the actual lab setup.
To prove that structure engineers emergence, we have to isolate it. We're testing whether increasing inference-time structure creates a critical stabilization threshold. And the kicker? We do this while keeping the model weights totally fixed and the available tools totally fixed. We hold the model constant and literally only turn the dial on structural constraints. I really want to emphasize this because it is absolutely crucial. This is not some speculative future casting. EP already operationalizes this claim as a falsifiable experiment. By using specific structure levels, what we call S0 through S4, we can actually detect stabilization thresholds. It's a completely measurable test for inference-level attractor formation. It essentially takes a highly theoretical concept and drops it right onto the lab table for empirical testing.
Let's walk up this high-tech structural staircase together. Down at step 1, S0, the system is unstructured. The agent just plans freely. Step up to S1 and we introduce a minimal template. Here it has to state a goal, its next action, a tool call, and a results summary. We step up again to S2, adding an explicit state table to track known info, missing info, available tools, and chosen actions. Then at S3, we throw branching and evaluation into the mix. And finally, at S4, we enforce recursive consistency and early stop rules. As you can see, we are systematically tightening the structural grip at every single level.
Now for Section 3, metrics under perturbation. This is where we start stress testing the system. Any true lab report requires rigorous stress testing, right? You can't just run a system under perfect conditions and declare victory. So, the experiment runs a task suite of multi-step, tool-using workflows, specifically designed to push these structural levels to their absolute limits. To do this, we actively perturb the tasks. We introduce paraphrase variations to test if the comprehension is stable. We inject completely irrelevant noise to see if the agent gets distracted. We leave out non-critical information, and we disperse key facts all over the prompt. And to ensure absolute experimental rigor, every single one of these perturbation conditions is repeated multiple times. We're literally trying to break the system's focus.
While the system is under all that stress, we are constantly watching our dashboard of tracked metrics. We're looking at things like success rate, tool misuse, loop rate, token consumption, completion steps, trajectory similarity, and failure mode entropy. But I really need you to hear this loud and clear. The point is not just getting one better answer. What we are looking for is a highly specific pattern among all these variables working together.
That brings us perfectly to Section 4, the S-star stabilization threshold, where we detect the phase transition.
This is where the data reveals something truly dramatic.
This is the exact moment we stop looking at a list of metrics and start looking at a phase transition. This is defined by our core rule, the S-star rule. A critical stabilization threshold, which we call S-star, exists if success jumps, trajectory similarity rises, and loops or tool misuse fall. But here is the most important word: simultaneously. They must all happen together at the exact same structural level.
What's really fascinating is how this threshold actually shows up in the metrics. When we hit that S-star level, the success rate just jumps up significantly. And right in tandem with that, trajectory similarity rises. The system isn't just succeeding more often, it's finding a reliable, coherent path to that success. It's the exact moment we can definitively say the system has entered a planning attractor basin. It's found a highly stable state of problem solving.
And at that exact simultaneous moment, the failures just drop off a cliff. The loop rate crashes down, tool misuse falls sharply, the failure modes actually become highly predictable, and erratic tool misuse essentially vanishes. Why? Because the structural constraints are actively holding the cognitive path in place.
Now, obviously, as scientists, we have to acknowledge every outcome. Even if a specific model doesn't show a massive sharp jump at a single S level, the experiment still produces a highly valuable monotonic stabilization curve. That just means it steadily and consistently improves in one direction. Whether we hit a sharp phase transition or a smooth, predictable curve, the experiment definitively proves the point. Structure is a measurable engineering variable, not just a philosophical slogan.
Finally, Section 5, Engineering Emergence Today. The Blueprint for Stable AI.
Let's bring our focus back from the lab environment to present-day reality. How does this high-tech experiment apply to building and deploying safe, reliable AI right now? Well, as enthusiastic as we are, we definitely must temper our expectations like true scientists. We need a guardrail here. We are not overstating that EP has magically solved every frontier-scale AI problem in existence, but the claim, and the hard proof, is that EP already achieves this structural mechanism conceptually, demonstratively, and experimentally, at the specific levels covered by this analysis.
So, the crucial takeaway here is that we've firmly proven our thesis. We no longer have to sit back and passively wait for emergence to happen on its own. Bigger models wait for emergence. EP already engineers the structural conditions that make emergence achievable, stable, and completely testable.
I want to leave you with a rather provocative thought to chew on as we wrap up this explainer. If AI emergence is no longer a total mystery, but is actually a measurable, falsifiable engineering variable today, how does this entirely rewrite the rules of global AI governance and safety? When we can actually test for stability thresholds, the future of structural intelligence looks incredibly bright. Thank you so much for joining me today. Keep questioning, keep learning, and I'll catch you next time.